This lecture is part of an introductory undergraduate course on complex analysis and will be about complex arithmetic. So I'm going to spend the first 3 or 4 lectures of this course just covering basic stuff like arithmetic and trig functions and so on before we get to the interesting stuff about complex analysis. So first of all, we recall what a complex number is. Well, if you're a computer, a complex number is an ordered pair of real numbers. So this is for computers. If you're a human, you write a complex number as x plus iy for a reason that will become rather obvious in a moment. So this is for humans. Writing it as an ordered pair xy is actually quite good for humans too, because this means you can identify complex numbers with the plane. You can just use x and y as plane coordinates. So you can represent each complex number as a point on the plane in much the same way you represent each real number as a point on the line. Now we need to define addition, subtraction and multiplication, and we'll do division a little bit later. So addition is completely obvious. Addition is just the same as for addition of vectors in the plane, so a plus ib times c plus id is just rather obviously given by a plus c plus I times b plus d. Multiplication is a little bit less obvious. If we write numbers as ordered pairs, then the rule for multiplication is given like this: ab times cd is equal to ac minus bd, ad plus bc. And this looks completely mysterious. You think, where on earth does this formula come from, and you can't possibly remember it. Well, if you write the numbers as a plus ib times c plus id, then it's much more obvious because you multiply this out and it's ac plus I squared bd plus ibc plus iad. And now we use the fact that I squared is, by definition, a square root of minus 1. So this is AC minus BD plus I times BC plus AD. So that's why we write numbers in this form rather than this form. It makes the multiplication of complex numbers trivial to remember. Now, what we really ought to do is to check that these satisfy the usual rules of algebra. So for example, we might want to check that a times b plus c is equal to ab plus ac, and ab times c is equal to a times bc, and so on. And there are several ways to do this. One, we can do a long, somewhat tedious check, which we're not going to bother because it's somewhat long and tedious. Secondly, you can go to an abstract algebra course. And in an abstract algebra course, you find that this definition of the complex numbers, which is often written as a C for complex numbers, can be defined. You take the ring of polynomials over the reals, polynomials in a variable I, and you quotient out by the ideal generated by I squared plus 1. And this gives a ring with this addition and multiplication, and there are general theorems in abstract algebra about quotienting out by these sorts of ideals, which mean this is automatically a ring. So if you go to an abstract algebra course, you don't have to bother doing this long check. The one thing I haven't yet mentioned is division, and this is a little bit less obvious. So we want to check that a plus ib has an inverse if it is not equal to 0, which of course stands for 0 plus 0i. And to do this, we're going to use complex conjugation. So complex conjugation takes x plus iy to x minus iy. And it's denoted by putting a bar over x plus iy. So this overline means complex conjugation. And the reason this turns up a lot is we've said I squared equals minus 1. But minus 1 actually is 2 square roots because minus I squared is also equal to minus 1. So when we talk about a square root of -1, we don't really know which square root, and in fact these two square roots are completely equivalent. And anything you can say about one square root, you can say about the other square root. So you can sort of flip from one square root to the other without really changing anything. So complex conjugation actually preserves all properties of the complex numbers. So for example, if we've got complex numbers z1, z2, and we take their complex conjugate, this is equal to z1 bar times z2 bar, and z1 plus z2 bar is equal to z1 bar plus z2 bar, and so on. In fact, the complex conjugation, z goes to z bar, is an automorphism of the complex numbers. This just means it's a map from the complex numbers to itself. It's a bijection and preserves all the structure you can think of. If you've done a Galois theory course, another way of saying this is the Galois group of the complex numbers over the reals has two elements, which are 1 and complex conjugation. So anyway, using complex conjugation, we can find the inverse of any complex number as follows. First of all, we notice that if we put z equals x plus iy, then z times its complex conjugate is real, because x plus iy times x minus iy is x squared plus y squared. And division by real numbers is easy. So we want to have 1 over z. Well, we don't really know how to divide by a complex number z yet, but we can multiply the top and the bottom by the complex conjugate. And now this division is easy because this bit here is now real. So let's carry this out. We have 1 over x plus iy. Well, this is x minus iy over x plus iy times x minus iy, which is equal to x minus iy over x squared plus y squared, which is equal to x over x squared plus y squared minus iy over x squared plus y squared. So this is the formula for the inverse of the complex number x plus iy. And of course you shouldn't waste time remembering this formula. What you should do is remember this trick of multiplying the numerator and denominator by the complex conjugate of the denominator. For example, let's just work out 1 plus 2i divided by 3 plus 4i. Well, as we said, we multiply the top and the bottom by the complex conjugate of this, so we get 1 plus 2i times 3 minus 4i divided by 3 plus 4i, 3 minus 4i. And now we can multiply out the top, and we get 11 plus 2i, and now we multiply out the bottom and we get 3 squared plus 4 squared, which is 25. So this is 11 over 25 plus 2 over 25 times I. So division of complex numbers is also reasonably easy. By the way, I should put in an awful warning here that there's a Greek letter xi, which kind of looks like this. And you must never use xi as the name of a complex variable, because if you do, you might end up having to take xi divided by the complex conjugate of xi. And if you write this out, well, we've got xi divided by the complex conjugate of xi, which wins the prize for the most awful mathematical notation of all time. Another useful property of complex numbers is the absolute value. So for a real number x, we know the absolute value of x is equal to x for x greater than 0 and minus x for x less than 0. And it's equal to the distance of x from 0. And we're going to define the absolute value of a complex number in the same way. So z is going to be the distance of z from 0. Well, that's easy to work out. So z is equal to x plus iy. And we're talking about the distance of z from 0 when we represent numbers as the plane. So we want to know the distance from the point xy to 0. And we know what this is by Pythagoras. It's just the square root of x squared plus y squared. And now we notice that this turned up when we were doing complex conjugates. So this is just the square root of z times z bar. And now we see that the absolute value of z1, z2 is equal to the absolute value of z1 times the absolute value of z2 because it's equal to this, and that obviously preserves that formula. We also get all the rules of absolute value. For instance, the absolute value of z1 minus z2 is less than or equal to the absolute value of z1 plus the absolute value of z2, because this just says the distance from z1 to z2 is at most the distance from z1 to 0 plus the distance from z2 to 0, which is obvious. So if we've got z1 here and z2 here, then this distance here is the absolute value of z1, and this distance here is the absolute value of z2, and this distance here is the absolute value of z1 minus z2. So most of the usual rules you're used to for absolute values of reals will also work for absolute values of complex numbers. If you've done metric spaces, you can make the complex numbers into a metric space in the obvious way. You just define the distance from z1 to z2 to be the absolute value of z1 minus z2, and this is just the same as the usual distance in the plane. So now let's see some applications of this. So let's first have an application to the following problem. Which integers are sums of two squares? So this is a very old problem in number theory, and it's quite complicated to work out the answer. We're not going to work out a complete answer, but what we notice is the integers that are sums of two squares are closed under multiplication. In other words, if you've got two integers which are sums of two squares, then so is their product. And the proof of this is as follows. Suppose we've got one integer which is a sum of two squares, and we multiply it by another integer which is the sum of two squares. Well, we can write this as a sum of two squares because it's AC minus BD squared plus AD plus BC squared. Well, that's a very neat proof, but where on earth does this formula come from? Well, it comes from complex numbers. So we notice that a squared plus b squared is equal to a plus ib. It's the square of the absolute value of a plus ib, and of course c squared plus d squared is equal to the absolute value of c plus id, all squared. So a squared plus b squared times c squared plus d squared is equal to the absolute value of a plus ib times c plus id, all squared. And we can now just multiply this out. This is equal to AC minus BD plus I times AD plus BC, all squared. And now x plus iy squared is just x squared plus y squared, so this is equal to AC minus BD squared plus AD plus BC squared. So complex numbers helps to explain this formula. I mean, of course you don't need complex numbers to prove this formula. You could just write it out. You can easily check it by multiplying it out, but that proof doesn't really explain why this formula exists, and it exists because of complex numbers. So let's just give an example of this. So we have 5 is equal to 1 squared plus 2 squared, and 13 is equal to 2 squared plus 3 squared. And we notice that 5 times 13 is 65, which is equal to 8 squared plus 1 squared. Well, it's also equal to 4 squared plus 7 squared. So why are there two ways to write 65 as a sum of two squares? Well, let's take a look. This corresponds to taking 1 plus 2i. So we notice the absolute value of 1 plus 2i squared is equal to 5, and this comes from looking at 2 plus 3i. So the absolute value of this squared is 13. So what we should do is multiply 1 plus 2i times 2 plus 3i, and this gives us 2 minus 6, which is equal to minus 4, plus 7i. So here we get the 4 squared plus 7 squared, or rather minus 4 squared plus 7 squared, but who cares? But there's another thing you can do, because you can change this to its complex conjugate. We can take 1 plus 2i times 2 minus 3i. And this is now slightly different, because we get this is equal to 8 plus i. And this one is giving you the other way of representing 65 as a sum of two squares. Of course, there are other things we could do. We could change this to 1 minus 2i, or we could use 2 minus i or something. But these would just give variations on these two formulas. We get things like 8 squared plus minus 1 squared and so on. So you see the two ways of writing 65 as a sum of two squares correspond to these two different products of complex numbers. So next application, let's take a look at Pythagoras' theorem, a squared plus b squared equals c squared. And we want to be able to find solutions to this. For example, everybody knows 3 squared plus 4 squared equals 5 squared, or 5 squared plus 12 squared equals 13 squared, and so on. And the question is, how can we generate lots of solutions to this easily? Well, let's suppose that a plus bi is equal to x plus iy squared for some x and y. Then a squared plus b squared is equal to the absolute value of x plus iy squared, all squared. So it's equal to x squared plus y squared squared. And here we've got a solution of a squared plus b squared equals something squared. So let's just try this. Let's try x plus iy equals 2 plus I. So 2 plus I squared is equal to 3 plus 4i, and 2 plus I absolute value squared is equal to 5. And this gives us the solution 3 squared plus 4 squared equals 5 squared. If we try 2 plus 3i, this is equal to the square of this is equal to minus 5 plus 12i, and we see that 5 squared plus 12 squared is equal to 2 squared plus 3 squared, which is equal to 13 squared. So you can just choose more or less any random complex number with integer coordinates and square it, and that will give you a solution of Pythagoras' equation. After people discovered you could extend the real numbers to the complex numbers, there were quite a number of attempts to extend the complex numbers to something even bigger by adding further variables, maybe the square root of something else. And people tried to, the complex numbers are two-dimensional, so several people tried to find a three-dimensional version of the complex numbers, and no one came up with anything very convincing. Hamilton found a four-dimensional version of the complex numbers called the Quaternions. So complex numbers are written as a plus bi, and the Quaternions need four variables. They're a plus bi plus cj plus dk. So these are the Quaternions. Quaternions means a collection of four things. And you need to know what are the products of these. So for the complex numbers, you just need I squared equals minus 1. The Quaternions, I squared equals minus 1. J squared is also minus 1, and K squared is minus 1. Well, you also need to know how to multiply I and J. Well, Ij is equal to K. And you might think that means Ji is equal to K, but no, this is equal to minus J times I. And Jk is equal to I, which is equal to minus Kj, and Ki equals J equals minus Ik. So, whoops, sorry, there's a minus sign there. So the Quaternions are not commutative. And this was very surprising at the time. I mean, these days we're used to multiplications being non-commutative. Matrix multiplication is non-commutative. But the Quaternions are one of the very first examples of something that was non-commutative. So it was a really big breakthrough to invent this. There's an old story that Hamilton was so excited by this that he carved the formula I squared equals j squared equals k squared equals ijk equals -1 on a bridge in Ireland. And anyone who believes this story has never actually tried carving a mathematical formula onto a stone bridge. I mean, you know, he might have scratched it on a bridge, but unless he happened to be walking around with a chisel and hammer, it's extremely unlikely he carved this formula on a bridge. Anyway, quaternions in many ways behave very much like complex numbers. For example, we found the inverse of a complex number, a plus ib, by multiplying the top and the bottom by the complex conjugate. And we can find the inverse of a quaternion in the same way. So if we take a quaternion, a plus bi plus cj plus dk, we define its quaternion conjugate to be a minus bi minus cj minus dk. And if we call this quaternion z, we find z times z bar is equal to a squared plus b squared plus c squared plus d squared. You might think you get a lot of cross terms from, we've got bc times ij plus bc times ji, and you think, what happened to this? Well, this is actually equal to 0 because ji is equal to minus ij, so all the cross terms vanish because of the non-commutativity. And so we can now work out the inverse of the quaternion, 1 over a plus bi plus cj plus dk is equal to a minus bi minus bj cj minus dk divided by a squared plus b squared plus c squared plus d squared. So this is just like finding the inverse of a complex number, except more so. And you notice that the denominator is non-zero for all non-zero quaternions. So all non-zero quaternions have inverses. There's also another thing you can do. So we showed the sum of two squares is a sum of two if two integers are the sums of two squares, then so is their product. Now for sums of three squares, this fails. So for example, 5 can be written as 0 squared plus 1 squared plus 2 squared, and 3 is equal to 1 squared plus 1 squared plus 1 squared, but 5 times 3, which is 15, is not a sum of a squared plus b squared plus c squared. So for sums of three squares, they're not closed under multiplication. However, sums of four squares are closed under multiplication. And we used complex numbers to show sums of two squares are closed under multiplication, and we can use quaternions to show that sums of four squares are closed under multiplication. So if we put z1 equals a1 plus b1i plus plus c1j plus d1k, then z1 absolute value squared is equal to a1 squared plus b1 squared plus c1 squared plus d1 squared, where the absolute value of a quaternion is of course defined as the square root of the quaternion times its conjugate. And similarly, if we put z2 equals a2 plus b2i plus c2j plus d2k, then we find z2 squared is equal to a2 squared plus b2 squared plus c2 squared plus d2 squared. And now we see that the product a1 squared and so on times a2 squared plus all of those is equal to the square root of the absolute value of z1, z2. And now you can multiply out z1 and z2, and it gives you something fairly complicated. So we get a1, a2 minus b1, b2 minus c1, c2, and then we get something times I plus something times j plus something times k, and you find that the square of this plus the square of this plus the square of this plus the square of this is the product of these two squares. I'll just leave it as an exercise to express the product of this number and the product of this number completely explicitly as a sum of expressions in all the A's, B's, C's and D's. Okay, so next lecture we're going to discuss multiplication and finding roots of complex numbers in a bit more detail. So for any for real numbers, it's obvious the square root is a complex number, and what we want to do is to show in particular that for any complex number, its square root is still a complex number.